And so on continuous loads that are under regular continued use, you will apply safety factors because those cables are under continuous current. You know, they're always on, they always have some heat in them. Their starting point is an elevated temperature as opposed to the non-continuous load that is usually off but occasionally turns on for no more than 3 hours. And so for non-continuous loads, you may not have the extra ampacity requirement that continuous loads have. So like with the solar array, you apply an extra 25% because it's a continuous load. And then you might also find yourself applying additional corrective factors. But if you think about it as, okay, is this a continuous load? Yes. Okay, I've applied my 25%. Well, have I adjusted for temperature? No. Okay, well, I still have to do that. You know, you start being able to understand all of the factors that need to go into your calculation. So which of these loads are continuous? You know, we have the refrigerator, the solar array, the washing machine, and the air conditioner unit. Now, your refrigerator might have a duty cycle where it clicks on and then it clicks off, and then it clicks on and then it clicks off. And the same thing with your air conditioner. You know, we already talked about the solar array. Now, really, the only non-continuous load in this list is the dishwasher, because it's not operating 24/7. I mean, that even though the refrigerator is going through a duty cycle, it's 24/7 operable. It doesn't just operate for 3 hours or less. Same thing with the air conditioner. Article 210.19, conductors, minimum ampacity and size. So we have branch circuits that are sized for not more than 600 volts. And then sometimes in code, there's other sections for circuits that are greater than 600 volts, which get into non-residential electric services. We can see a reference later in the code for sizing. We can see references later in the code for motor circuits. And then we see a voltage drop requirement that says voltage drop should not exceed 3% at the furthest load or 5% to the furthest outlet. Well, in the solar industry, we're usually designing for a 2% voltage drop or less. So we're upsizing our cables for voltage drop, and we would never, we would not violate this code. And, you know, it's usually cost effective to spend a little bit more money on cable and make it up in efficiency gain. So, yeah, not trying to get the 5%, but going for a 2%. Is kind of the more sane, rational approach. And since we're on the topic of voltage drop, what does a 5% to the furthest outlet? Now, what would that mean for AC or DC circuits? I put DC in there, but actually AC is less efficient than DC. You know, DC goes from that high potential all the way down the mountain to its low potential. AC wiggles back and forth. And that wiggling produces a little bit more heat, a little bit more resistance. And so actually you'll get, if it's the same voltage level, the same cable, the same conductor on AC versus DC, the AC system will just produce ever so slightly less power. So what does this mean? What does a 5% voltage drop really mean? Well, what I'm thinking about is tiny homes or RVs. People say, well, I want to convert my clubhouse or my tree house or my hunting cabin or hunting shack into a solar array, and I want to run it off a 12-volt battery. Well, if we're using number 8 copper at 12 volts, I'm going to exceed a 5% voltage drop anything outside of a 20-foot perimeter of that battery bank. You know, if I'm using number 8 copper, which is pretty, you know, that usually is about the maximum size you go up to before the components may not, you know, lower power components may not accept larger cable than that. And so, you know, it might work for a recreational vehicle that's no more than 40 foot long to have a 24-volt battery bank. But then if you want to do a off-grid house, and it's not a tiny house, but it's an actual house, you know, it's not a yurt, but it's a home that most people would be familiar with, you know, want to be comfortable living with, you wouldn't want to have that be a 48-volt battery bank where you're just running it off of DC only circuits. And it doesn't have anything to do with the DC, whether it's DC or AC really, although finding equipment might be hard if you're running at oddball DC circuits. It's really more to do with the low voltage of a 48-volt battery bank. We want to step that voltage up so that we can push it further. So your 120-volt circuits and your AC service panel can push electricity a lot further than a lower voltage DC circuit. All right, let's define a term. Feeder. All circuit conductors between the service equipment, the source of a separately derived system, or other power supply source and final branch circuit over current device. So what we're talking about is anything between the generator and the breaker switch on the panel that the generator provides. That's a feeder circuit. Similarly, your grid connection is the same. It's from the grid to your main service panel. That's a feeder circuit. So from power sources to the feeder, the main service panel, the load panel that they supply, that's considered to be a feeder circuit. And so where's the feeder circuit on this graph? Well, here's our in-phase microinverter AC branch circuit. And then it's landing on our load panel. We actually have two feeder circuits on this. We have the feeder circuit from the utility coming in, and then we have the feeder circuit from the solar array coming in to the bottom of the bus bar. And so now we're getting into section 200, and we've defined all of our terms, and we've talked about clearance requirements and general installation rules and regs. And now we're getting into how do we supply power to our load. And it says we have different rules for feeder panels of 600 volts and lower versus larger commercial systems. When you get into those above 600 volt systems, you may have less requirement in some areas because you also have more requirements in others. So there may be a requirement for an engineering calculation. There may be a requirement for rigid metal conduit. There may be a requirement for, I don't know, additional protective relays. And so that might be, you also gain some cost efficiencies of using higher voltage equipment. And so that's great too. You know, so when you get into higher voltage equipment, there are perhaps some cost savings on the overall system, even though individual components are, you're spending more money on that, and you'd have to buy different things for higher voltage commercial systems. But anyway, feeders that are under 600 volts are sized on 125% of the continuous load plus the non-continuous load. So the continuous load, because it's under full-time operation, gets adjusted a bit more than what a non-continuous load would do. Overcurrent protection. Feeders are protected against overcurrent by an overcurrent protection device. And so what is an overcurrent protection device? It can be a couple of things. You know, what we're familiar with are breakers on our electric service panel. Those 20 amp breakers go over 20 amps. That's an overcurrent protection device. But a fuse is also an overcurrent protection device. And so a fuse, as opposed to a breaker, will burn up and not work rather than just trip. You might say, well, why would I want a one-time use fuse rather than a breaker? And the answer is, well, cost. You know, it's not going to happen. If it does happen, you want to know why it happened anyway before you really operate it again. A fuse may be perfect for the job, although breakers may be more simple. It also might cost more. Regardless of whether you use a fuse or a breaker, you're using an overcurrent protection device. And so if you have one circuit and there's a fuse on one end and there's a breaker on another, that circuit has two overcurrent protection devices, and it's a little bit redundant and not necessary in most cases. Let's keep going. Get into some more definitions. Ground is the earth. Grounded is connected to ground or to a conductive body that extends to ground. And the equipment ground conductor is the conductive path installed to connect non-current carrying metal parts to the system grounded conductor or to the grounding electrode conductor, or both. So very quickly into the section 200 and 300, we're going to have these terms coming at us: the neutral wire, the grounded conductor, you know, a ground plate, a ground rod. And it's important to understand what these are. And for now, just the equipment grounding conductor, the EGC. So the equipment ground conductor is the path that is put in place to connect metal parts of your system to ground. So if you have a metal box, if you have a metal fitting, if you have a metal bar inside your plastic box, you know, your metal module frames, your metal racking systems, you know, all metal parts have to be connected to ground. And the system in the building that connects those metal parts to ground is called the equipment ground conductor. And so what's ground in this picture versus the equipment ground conductor? Well, we got, you know, here's our ground. This is our connection to ground. And our equipment ground conductor is this green wire that is connecting to our microinverter box and connecting to our modules. And this can be a few things. This could be copper wire that is landing on a ground lug between module to module to module. The racking system itself may be listed as a ground path. And so you might have a grounding washer that connects the module frame and the microinverter to the racking system. And the racking system may land on a box that has a bare copper or green wire going up to the rooftop. So this green system, how the all metal parts are connected together is part of your equipment grounding conductor system. And then the ground is down here at the bottom. So where did my slide go? There we go. So then we have the grounding electrode conductor. And then another term, the service conductors and the service point. And so what is the grounding electrode and the grounding electrode conductor? The grounding electrode is the object that establishes the direct connection to ground. So whatever this, you may be familiar with this little triangular symbol as ground, but whatever that physically is on the job site is the grounding electrode. And we have a special term for this cable that connects the ground to actual ground. This kind of end of the line cable that goes directly to the physical object that connects to ground is the grounding electrode conductor. And so the question is, well, how is the equipment ground conductor separate from the grounding electrode conductor? One's an EGC and the other's a GEC, and they have the same words. So what are both? And the answer is, well, they're both very similar, but this one wire is kind of the end of the line. And so whereas the equipment ground conductor may be sized for each individual component along this circuit, the grounding electroconductor is sized for everything. So it's going to be sized off the service itself and be a little bit thicker and have some unique safety requirements to it. And so, you may need a system ground, an equipment ground conductor, a grounding electrode conductor, and you may have we really haven't gotten yet to the grounded system conductor, service conductors. What's the service conductor and the service point? Service conductors are the conductors from the service point to the service disconnecting means, and the service point is the connection between the facility serving utility and the premise wiring. And so here we have our electric meter, and then we have our premise wiring, and often that meter is considered the disconnect and the service point. And so the service conductors are coming from the service point to the service disconnecting means. So they may be talking about from the transformer up to that meter itself, and then the point of the connection between the facilities of the utility and the premise wiring being the service point. And usually it's governed at that meter. We get another definition. We're going to say feeders shall not be derived from auto transformers unless the system supplied has a grounded conductor that is electrically connected to the auto transformer grounded conductor. All right, so what the heck does that mean, and how does it apply to solar? I've never seen an auto transformer in a solar array until I started to get into battery banks. And so here, SMA has a very popular auto transformer, and it needs one because, if my voice gets too squeaky, just send me a message and I'll take a sip of water. But it needs one because the SMA battery inverter is designed for 120 volts. And if it's going to be grid connected, that voltage needs to step up to 240 volts. And so it's a grid connected inverter that has a 120 volt output, and we need to step that voltage up to 240 volts for it to be compatible. And so here is our battery inverter, and here's our transformer and distribution box, where we are taking the output of the Sunny Island and turning it into a 240 volt leg 1, leg 2 neutral output. And so going back to the code, we have a feeder circuit from the battery bank supplying power to our load through this auto transformer. So what do we have to do? The system grounded conductor needs to be electrically connected to the auto transformer grounded conductor. We still don't know what this grounded conductor is. We haven't defined it yet. A grounded conductor is a system or a circuit that is intentionally grounded. So a grounded conductor is like this green conductor that is intentionally connected to ground. So is this the only grounded conductor in the system? what we're talking about in this case, when they refer to a grounded conductor, is this neutral wire. So we see this neutral wire that is connecting to the sunny island, to the neutral of the sunny boy, to the neutral coming in from the electric grid, maybe even from the neutral of this generator. They're all sharing a common neutral. And the reason for that is that the neutral will help all of the breakers and overcurrent protection devices in the system work. The neutral is not a zero voltage system. The neutral is a helps complete the circuit for these systems, and if there's ever a ground fault, the current in the neutral helps lift the breaker at the breaker switch. And so here we have our sunny island, and it says, feeders shall not be derived unless the grounded conductor is electrically connected to the auto transformer. You may need to share, tie in the neutrals together of all these systems. And then there's going to be a rule on how that neutral is connected to ground later. So the neutral is a grounded conductor, but where it connects to ground is governed by very specific rules. And so the point is, you may have a generator providing its own neutral. You may have the utility providing their own neutral. You may have a transfer switch and a solar array. And if these are all going to be operating on a shared, on a non-separately derived circuit, their neutral system has to be interconnected. So then we have voltage mandates that says unless there's special conditions, in the United States, we're going to use nominal voltages of 120, 120, 240, 208, 120, 240, 347, 480, 277. There's nickname voltages. And we say we're going to rally behind all these specific voltages. And that really has nothing more to do than tradition and, the physical internals of the electrical components, namely the transformers that govern our electric grid. So here we have a 220 volt branch circuit service. This is 120, 240 volt split phase. And so all we have, the reason why we use this 120, 240 volt residential electric service is simply this is the common transformer that the windings inside the transformer are specifically designed to make it, and it's just the standard that we use, and it's how we step down our medium voltage from the power lines that may be operating at 2,400 volts, how we step that down to 240 volts, and then again to the 120 volt circuits inside our home. Now, in our home, we have single pole breakers that are 120 volt circuits, and then we have double pole breakers that occupy 2 breaker slots, and those are for our higher voltage appliances, like maybe your dryer circuit is on a 240 volt device. Maybe a deep freeze might be on a 240 volt device. It'll just take and be designed for a little bit more powerful electricity, electricity that operates at a little bit higher pressure and can push more electrons through a conductor than a 120 volt circuit can. All right, let's study this picture. This is something I definitely was scared of when I got into the solar industry, because often you'll be designing your home and the utility will want you to install the meter box and the masthead and the weatherhead and even put in conductors all the way up to this point. And then the utility will come along when they establish a new electric service. You have your higher voltage power lines coming in from the utility, and then they pick out a transformer for your electric service. In this case, it's a 240 volt split phase. And what we can see here is that the utility's neutral is actually going into the transformer too. This transformer circuit is grounded at the bottom of this pole. And then the utility conductors come along this wire and then get taped up into the masthead. Now, I've seen situations where the utility has come out during an install and installed the transformer and these power lines ahead of our commissioning, and they taped up the wires that were hot, and I've seen these wires sway in the wind and touch the side of a metal building and cause a ground fault that kind of blew apart some connectors on my grounded solar array. You know, you always have to be aware of what's going on during an interconnection process because these wires are hot. There's no off switch to these power lines at this point. You know, there's a little switch right up here at this fuse. You know, often when the utility wants to simulate a power outage on site, they're going to come in and with a pole and kind of poke this fuse up so that the transformer loses power, and they'll sense a power outage and see that the solar array turns off. This weatherhead is to keep rain out of this service box. You know, if this was up, rainwater could, you know, this drip loop here will prevent rainwater from getting into the meter in the meter box. So then we get to we've talked about what is a neutral conductor. And this says the conductor connected to the neutral point of the system that is intended to carry current under normal conditions. So the neutral conductor is a current carrying conductor. It is intended to carry current. The equipment ground conductor that connects all the metal parts together on your building is not intended to carry current. The neutral conductor is intended to carry current under normal operating conditions. And depending on your transformer, your electric service conductors are going to be slightly different from each other. So here we have a 120 volt single phase, 240 volt single phase, and then 120, 240 volt split phase. And so they are actually all different. A 120, 240 volt split phase is different than a 240 volt where you just have a single leg to ground. A 120 volt service is different than a 240 volt split phase. And then you get into three-phase services, and the windings start to look even more complicated, and they have different terms for it, and it really just depends on the utility, on which transformer they want to install, or what kind of motor you're trying to drive. But there's delta services and Y services, and you know, at any point the neutral wire is supposed to be, you know, it's going to be balancing out and connected to ground at one point. For branch circuits, we're still defining things. So once we get into breaker sizings, we'll better understand the role of the neutral wire. Branch circuit feeders and service calculations, fractions of an ampere, calculations shall be permitted to be rounded down to the nearest whole amp with decimal fractions smaller than 0.5 dropped. And so you might be brand new to performing calculations, and you know, maybe you took some engineering courses in college where you get the concept of significant digits driven home, and you might try and capture all the significant digits possible so you can carry your voltage and amperage calculations out to the 0.001 level. Code is trying to keep the design work. It bridges that gap between the Poindexter and the pragmatic off-the-shelf product. You can do engineering calculations in code, and maybe engineering calculations even when not mandated, such as there commonly are at higher voltage, over 600 voltage calculations. Maybe doing an engineering calculation and calculating the exact operating conditions can show that you can get away with a smaller conductor size. But generally in those circumstances, you're going to be, erring on the side of oversizing than undersizing. We see these 25% additional correction factors. We'll see temperature correction factors come into code that are all erring on the side of caution. And so I guess by the time we get to the final decimal and rounding the system, they say, all right, you can any decimals of amps, any fractions of amps, just round down. And I don't understand the last part. It says you can round down to the nearest whole amp with decimal fractions smaller than 0.5 dropped. I guess that's referring to if you're doing multiple steps in the calculation, how precise you need to go with your calculations. And you will have specific calculations for every specific kind of power device in code. So especially for your perhaps non-continuous loads like dryers and range stoves, or commonly found loads like lighting loads or receptacle loads, have different rules, as well as separate rules for dwelling units versus non-dwelling units. Like a home where people are living full time is subject to more stringent regulation than, say, a warehouse. But that's so we'll visit some of those special calculations as we get into section 400, which is general equipment, and then again when we get into section 600, which is specialty equipment. It says the minimum load of a feeder is the sum of all the loads determined by Part 2 after any applicable demand factors permitted by Part 3, 4, or 5 of Section 220 are applied. And so we have to go a little bit further into this, but basically, you take your load of your feeder service, and then you have correction factors that you need to apply before you get to your final calculation. If you're adding on a section of a building to an existing installation, you may have different requirements than new construction. What's the minimum circuit size that you have to allow for a dryer or for an outlet? Let's kind of accelerate some of the content along here. Got another definition. The authority having jurisdiction, an organization, office, or individual responsible for enforcing the requirements of a code or standard, or for approving equipment, materials, and installation or procedure. So the authority having jurisdiction has final say over what code is used. Remember, National Electric Code is a private industry standard that is not designed to be a design manual. And so your local authorities have complete power to go beyond electric code in terms of having additional requirements. And what's very common is that your local authority will want to have a disconnect switch on the outside of the building that is a very clear and straightforward and easily to see from a distance disconnect switch. And so they're settling on a knife switch disconnect, and it's not part of National Electric Code. So whenever you're doing any kind of solar design, if you design to National Electric Code, you can still make design errors and fail your inspection because there may be additional jurisdictional requirements that you have to abide by. And so where do you go and find what your local jurisdiction is? Well, the Desire website is a good starting point. You can go up and look at the interconnection standards in your area, and usually that will lead you to contact information on who to follow up with to determine who the utility is in your area and what the interconnection requirements are. Back on what are these correction factors when we're sizing our feeder circuits. We have different correction factors for lighting circuits, motors, space heating. Let's just look at space heating as an example. Rather than being calculated at 100%, when managing your energy, the local AHJ can allow feeders and service conductors to have less than 100%, provided the conductors have the ampacity for the load so determined. And so, what this is saying is, there may be areas where if you're employing on-site energy storage, like with a battery bank, that your electric service may be allowed to be undersized. We've seen that happen with electric space heaters. And also we see some undersizing allowances based on, the larger of a usage that you're having. So if you have an apartment complex and you're sizing the utility service to go into the complex, the more homes there are, the more stoves there are inside the home, means that they assume not all of these things are going to be on at the same time. And so you can discount it further if you want to. Again, it's a minimum design standard. So on a home, for your house, where you only have one or two of a common appliance, you get all the way up to a 48 kilowatt service panel, and it's very hard. Even if you go and turn on all the appliances in your home, it's very hard to blow the power in your service panel. But you might have buildings, if everyone's running their air conditioning at the same time, you might get into a whole complex or even a utility distribution circuit experiencing some overloading and having the main breaker switch when you get into too many discount factors applied. The feeder or service neutral load, the maximum unbalanced load, is the maximum net load between any neutral conductor and any one ungrounded conductor. And so we know that the neutral conductor is a grounded conductor that is intentionally grounded at the point at one point. We're gonna worry about that later. But it says the maximum unbalanced load of the system, which is the load that is applied to the neutral, is the maximum net load between any neutral conductor and any one ungrounded conductor. And what that means is the neutral needs to be the same size as the ungrounded conductors, your leg 1, sometimes leg 2, or leg 3 of power. And then from beyond that, they say, well, under certain conditions, you can reduce the neutral, and under other conditions, you can't. So as a starting point with your design work, if you don't want to make any mistake, don't undersize the neutral, and what that'll, then you'll be in the clear. If you do undersize the neutral, you may save a little bit of money, but not as much money as a design mistake. You know, if you want to go ahead and do all of your conduit calculations for a full-size neutral, you're not going to have any design changes if, when it comes time to order the material, your supplier comes back and says, well, actually, you know, you usually undersize the neutral in this location and you decide to do a design change. But if you're just beginning, don't undersize the neutral for now. Optional service load calcs, dwelling units, feeders, and service loads. There are other ways to calculate how much power you need to give to dwelling units. And so what we see here is 10 kilowatts for general service, and then 3 watts a square foot for lighting for 40% of the home. And then for every 20 amp branch circuit, you throw on an additional 1.5 kilowatts. And then you do 100% of the continuous load ratings for, you know, your appliances, cooking equipment, dryers, water heaters, motors, you know, stuff that is your non-continuous loads. And then you have your heating and air conditioning loads. You know, they say, well, you're not using both at the same time. So, you know, what's your maximum load in the spring, or what's your maximum load in the winter between the two pieces of equipment, and design off that. And so there are some, you know, in terms of establishing the minimum service for your home, you know, there are some general rules to go by. And generally, these rules will get you into, you know, a 100 amp service for a small unit, and then 200 amp service for a large unit. It also might mean that if we're generating energy on site and we are managing our energy with a battery bank, that some of our home electric services are going to start to look pretty oversized compared to, you know, if you're an energy efficient home and you're fine tuning your energy use, you know, you might find that your home is only using 60 amps of power, but you have a 200 amp electric service. Let's see. So how do you determine your existing loads? You're actually allowed on existing constructions to base your load calculations off of real monitored usage. And so, you know, you generally will use a 1 year period of load. And if you don't have 1 year, you base the maximum 15-minute demand using the highest air conditioning or heating load over the past 30 days. Now, where this is relevant to on-site power systems is sometimes your utility will establish a maximum size that you are allowed to interconnect to the grid based on your 1 year load usage. And, you know, I've heard that, you know, when it's kind of interesting. You go to net metering. They say, well, you can't have a system that will offset more than 100% of your energy use. But I've also seen requirements where they also say you can't do an array that will offset substantially more than your power. So I had a client who wanted to do a 50 kilowatt array, and he had, you know, that would be like on a 40 kilowatt inverter. And he has a 48 kilowatt electric service, you know, 200 amps times 240 volts. A volt times an amp is 48 kilowatts. And so he wants to max out his service connection and do the largest possible array he can and just sell back a lot of the electricity to the grid at wholesale pricing. And the utility comes back to him and they say, you don't have the load to accommodate a 48 kilowatt array. And so before they go and review that, before that process comes in, you may actually want to go around and turn on all the circuits in your home at the hottest time of the day for a 30-minute window under a residential service, just so that you can spike your load all the way up to its maximum, so that when the utility reviews your electric use, They can't come back and say, well, your load doesn't get anywhere above 16 kilowatts, so a 48 kilowatt array is way oversized for your use. You know, you may there may be some reasons for you to go and juice your demand so that you can not just reduce the minimum service size, that the minimum that needs to be established. There may be reasons to go and go way beyond that and go up to the maximum service size